anybody ever played around with anything like spatial computing, like CFD, fluid dynamics, computational fluid dynamics?
Not really. I've done a two-dimensional heat equation. I think that's about it.
That's out of my league probably anyway. I was just curious. It seems like it'd be good for it because I mean, what I know about it, I used to work at an aerospace place. I mean, they'll calculate every point around the surface of a wing, say, for instance, and then they go back and calculate every point past that and every point past that. And they just have to.
Yeah, and that's exactly the kind of problem where if you had each of those calculations being performed in parallel by some local system, you can get a huge performance.
Yeah, it seems like they can propagate quickly.
Definitely, and that's what happens with the heat equation. It's a purely local calculation based on the temperature of neighboring elements, your temperature, and the material properties where you're located. Very easy calculation, but if you have to do it across, a million by a million cells, it's computationally time-consuming. Okay, so any other questions from last week? I should repeat something that I just commented a minute ago. In addition to the simulator, there's also an API available for the simulation engine. If you decided you wanted to do some experimenting at a sort of lower level than just the simulator itself, if you wanted to, for example, read a JPEG file, take the bits from an image and feed them into a distributed processor of cells, that's available through the API. It's basically a set of Java calls that you manipulate cells, inputs, outputs, and the clock directly through system calls instead of actually using the simulator front end. And so if that's interesting to you, let me know and I can give you details. Okay, so I wanted to talk about homework 2, which most of you attempted, and all of you pretty much got the idea of what the circuit is doing functionally. It's one cell was reading another non-destructively. Some of you also got sort of a second level of functional behavior here. So basically we had two cells. This one takes an input from the north that's used to control the mode of this cell, 0, 1. Bits coming out of here are fed back in and also sent out to the western output of 0, 0. So that's just our standard non-destructive cell reader. And then there were 3 different circuits depending on which truth table you had in this cell over here on the right. Okay, in the first one, north, south, west, east were all equal to 1. This is what your truth table looks like. So when you start this circuit, and you start it by basically putting a 1 in here, this cell goes into C mode. Each tick of the system clock, one of these bits of the truth table is read out and sent through 0, 0 data west out. In the truth table, it starts over here and it reads these 4 bits, these 4, these 4. So this circuit is outputting a 1 for the first 64 system ticks. And after the 64th tick,
why we start from DW?
That's just the order that the simulator is using. This is bit 0, 1, 2, 3, 4, 5, 6, 7, 61, 62, 63, 64, and then the 65th bit is over here. Okay, it's a fairly arbitrary distinction, but for the rest of this course, this will be the ordering that will apply for 4-sided cells. Okay, so all the D bits come out first, and then all the C bits. So if you run this on the simulator, you'll see the first 64 clock ticks, you get 1s, and the next 64 ticks, you get all 0s. And then it repeats, 64 1s, 64 0s. And so this is outputting a repeating pattern of 1s and 0s, and basically it's one big long pulse. It goes high for half of a programming cycle, and then it goes low for half of a programming cycle. And it repeats indefinitely as long as data north in is 1. Okay, the second circuit is similar. Had 1s in these 2 columns and these 2 columns, and you can see what's going to happen. You're going to get out 0, 0, 1, 1, 0, 0, 1, 1, and so you get a repeating pattern, but it's a different pattern. And it basically changes every 2 system clock ticks. So this is being output at 1/4 the system clock frequency. Okay, so every 2 pulses per programming cycle. And in the third example, we basically alternated 1s and 0s in the truth table columns, and the bit pattern that comes out of there is 0, 1, 0, 1, 0, 1. So it's just an alternating pattern of 1s and 0s, and that's basically coming out at half the system clock frequency. Okay, so what we're talking about here is basically tying together D mode and C mode. Because C mode, where you're configuring cells, you need to feed in bits on the edges of the system clock. And D mode, I've said, completely ignores the system clock. So how can a D mode circuit program a C mode cell? You need to have some way to connect those 2 modes. You need to have a D mode able to look at the system clock. And this is the kind of circuit that you use to do it, because you're definitely outputting from this D mode circuit on the left in synchronization with this single universal system clock. Okay, so circuits like this are called crystals. That cell on the right, where you have a truth table and you're only using it to store a bit pattern, we call that a crystal. Okay, it's just a regular cell, but we're not really interested in what the function is that that cell would perform in D mode. We're only interested in the pattern of bits inside it. And the cell on the left, which is controlling it, we just call that a crystal controller. Just sort of some terminology. And again, they're basically a way for D mode cells to get some sort of interaction with the system clock. Now, that last circuit, circuit 3, where you alternated 1s and 0s, that's coming out at half the system clock frequency. Okay, the system clock, each time that the edge falls, the truth table position that you're reading changes by 1 spot, and so on the falling edge, you change value in the output. Okay, and that's exactly half the frequency. Okay, are you familiar with this circuit? Seen one of these before? That's a no. Okay. So what does this circuit do? It takes an input A, it feeds it into an exclusive OR. It also runs it through a delay circuit, which in the matrix could just be a couple of cells that just feed input to output. And then it takes the delayed version and feeds that into the B input. So here's your original input A, and it's just some oscillating regular signal. If you delay it, it basically just shifts it over by a little bit in time. And if you exclusive OR those, what you find is that every time that these 2 signals differ, you get a pulse. That's what an XOR does, a 1, 0 or 0, 1, gives you an output. So this one changes and this one hasn't caught up yet, you get a pulse. This one drops and this one is still high, you get another pulse. And if you compare that to the system clock, you see that you're getting pulses out at the same frequency as the system clock. Okay, this is a frequency doubler. You can put in a regular pulse train and it basically doubles its frequency. And you can use this to bump up that last crystal to a circuit that generates pulses in sync with the system clock itself. Okay, so now we can actually generate D mode outputs that are synchronized with this C mode controlling clock. And the pulse width and the phase and so on of this output is different from the system clock, but you can actually condition that and you can square it up.
Usually double the clock processing.
So this is your input to this circuit, and this is the output.
Oh, yeah.
Okay, and the thing is, this is outputting a pulse every time that this changes value. So pulse, 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 pulse. So it doubles.
In regular circuit, I suppose you use buffers for the delay?
You use buffers for the delay, yeah.
With the cells, how would you implement that?
If you go through a cell, there's a delay.
So you're just going to stack a bunch of cells and just...
Yeah, you can like serpentine down and come back up, or, you know, you actually only need a 1 cell delay. Now, in combinatorial circuit design, this is called a critical race. Okay, it's a race condition. It depends how quickly A moves over here versus how quickly it moves over there. And in general, you're supposed to avoid race conditions in your circuits. But in this case, you're actually deliberately setting up a race where you know who's going to win. You know the circuit's going to get the input at A before it gets it at B. And you can take advantage of that. In a VLSI circuit, you could probably just introduce some capacitance on the line. put an extra layer on top, so there's a capacitive gate that needs to be charged up, and you can slow down your circuit like that. So there's all kinds of techniques. Okay, some other useful crystals. So this one, we have a single 1-bit in the truth table. We just AND all of the inputs and use that for data west, so you have a single 1 right here. And when you use this crystal, you're going to get out a 1 followed by 127 zeros. And so you get a single 1 at the beginning of each programming cycle. And I put this question down here, what do we actually mean by the beginning of a programming cycle? Because cells can go in and out of C mode more or less at will. They don't all move into C mode at the same time. It's strictly when their C input goes from 0 to 1. So there's not really a programming cycle where you can talk about the beginning of it. But we're sort of thinking relative to some sort of beginning time, T0. And usually what you're doing when you build larger circuits and you're using C mode and you're using ways to tie into the clock, you have your own internal system clock that you're building. And you're driving it off of a circuit such as something with a controller and a crystal. And you try to keep everything sort of running on the same 128-tick programming cycle. But it's purely a convention that you make up while you're designing your own circuit. It's not inherent to the system itself. Okay, there's just one big long clock. It's not natively broken up into 128-bit pieces. Okay, this is a slightly different circuit, slightly different crystal. In this case, we output a 1 when all of the inputs are 0. We output 1 to control north. And if you go through this, you'll get 127 zeros and then a single 1 at the end of a 128-tick programming cycle. That's actually a little more useful because at the 128th tick, this output will rise and then it'll drop on the next system clock. And so you can use that drop to sort of trigger some event that you want to synchronize in programming cycles. But there's something else useful about discussing this particular crystal. So some more terminology. There's this notion of a live cell. Okay, a live cell is a cell that has any 1s in any of its C output columns. And what it means is that this cell could potentially be configuring other cells. There's some condition under which this cell could output a C mode, a C line, to a neighbor. So if all of the C outputs are 0, that's just sort of a regular cell. If any of them are 1, we call that a live cell. And it means you need to be a little careful about it because there's a chance it's going to start doing configuration on neighbors. For crystals, again, we don't really care about the function that a crystal is implementing. We just care about its bit pattern. And so a crystal that's also live is something that needs to be you need to handle it a little carefully. So one way to do this is with something called a guard cell. This is basically the same circuit as before, except we always put a 1 into the C input over here. And so this crystal, which normally would put a 1 out to its control south, well, it's not going to because this is going to be in C mode. And a C mode cell does not assert any of its C outputs. Okay, when you're in C mode, all your C outputs are 0, and all the D outputs on non-active sides are also 0. So once this thing goes into C mode, this drops to 0. And now this is not going to configure any of its neighbors. Okay, and by keeping this permanently in C mode, this cell is in some sense under control. Okay, so that's why we call it guarded. So this would be a guard cell controlling this crystal. And that's a safe way to implement sort of an arbitrary truth table.
But then the guard cell could reduce some of the functionality in terms of timing.
No, go ahead.
I was just saying, maybe you want to start grabbing the truth table at a certain point,
Right.
Whereas this guard cell would constantly be out.
Exactly. So that is one issue. You don't get to choose when you begin reading the truth table. So you need to have some way, unless you're just doing a very simple repeated pattern, you need to have some way of knowing when this cell began asserting a 1. Okay? And that's actually a really interesting question. And it turns out it works out well. Depending on how you build the circuit, how you bootstrap. You do everything in 128 tick cycles. So that'll actually work out well, but it's a good question to keep in mind. Okay, now a slightly more interesting case than this one. Oh yeah, so I've mentioned this last time. Guard cells are basically like backslashes in Java. They basically tell the matrix, this is just data. Okay, don't interpret it as code. Don't let it do anything. Just treat it as data. And it's exactly like doing a backslash followed by a double quote. This tells the interpreter, this is just a character. It's not the beginning of a literal string. It's just a character. It's just an ASCII code. Okay, that's basically what a guard cell is doing. It's saying, this is not something that configures cells to the south. It's just a bit pattern in its truth table. Okay, it changes the interpretation of it. Okay, so here's a slightly different case where we have a crystal, and the crystal's function says send a 1 into the control west output. And we have a guard cell which is permanently putting that into C mode. But the question is, which of these cells is going to be in C mode? Because, well, this is trying to put this in C mode, this is also trying to put this in C mode. And if this succeeds, this thing's C output will drop. Right? C mode cells, C outputs are always 0. In which case, this would be in C mode, and this would be performing its function. So what happens in this case? Well, in the simulator, it may just oscillate, depending on how you build this circuit. In real-life hardware, it's a race. And one of these will go into C mode first, and the other one will stay in D mode. But how do you control that? How do you actually enforce that the cell on the left is the guard cell? So there's just a sort of convention that we use. We can call it the Northwest Convention. And the idea is we always try to configure cells from the north or from the west. Okay, and you can't always do this, but for the most part, if you're going to put a cell in C mode, try to do it from over here or from up above. And it's just a convention, but if you stick to that convention, for example, when you're bootstrapping, you would bootstrap from west to east and from north to south. And by going in that order, you ensure that you place the guard cell before the crystal. Okay, you would configure this cell first, and then you would place this one. Once you place this one, though, it's outputting its C output. And then when you configure this cell, this is going to go into C mode before it has a chance to come back and try to configure the guard cell. Okay, so that's just something to keep in mind, and we'll definitely go through some more examples of that when we're bootstrapping and configuring large sections of cells. But it's just a sort of useful convention that, in general, you would not want to configure a cell from this side, for example. Because if you're bootstrapping in this direction, you would be placing the crystal before the controller.
Are we giving priority to either west, east, over north, south, or the other way around?
I don't think you have to, no. You just sort of need both of those, but I don't think I've ever encountered a case where you had to choose one over the other. Okay, other things that you can do for dealing with live cells, the easiest way is just to leave some empty space around a crystal if it's got the potential for going live. So in that case where it was putting a 1 out to its control south output, if you sort of leave the cell to the south flank, then that control south output does no harm. Okay, its data south out will be 0, so even if it asserts its control south output, it's just going to take an empty cell, configure it to be empty. So that's sort of the easiest way, is just leave a little space around the live sides of the cell. You can also avoid live cells completely, and we'll go into the details of this later, but basically live cells can be kind of expensive. In simulation, they're very expensive. They slow down the simulation a lot because things happen every clock cycle tick. Okay, things need to be adjusted in the cells. So in simulation, we sort of try to avoid C mode cells as much as possible. In hardware, at least under silicon implementations, C mode cells are going to be more power consuming because there's things changing every clock tick, whereas D mode cells may be totally static until an input changes. You can avoid C mode cells in a lot of cases by using 2 cells to hold the cell's truth table. You basically use one cell and you store the D columns, and you use another cell and you store the C columns, but you store them both under the D part of the truth table. and then you put those together when you want to extract the full C and D truth table.